Okay, so I think we'll start. So in this lecture, I'll present a quick general overview of the field of self-driving cars. We'll talk briefly about the social perspective, the different actors, the road so far and the road ahead. Since it's so far out in the semester, this won't be a very technical lecture, so it's meant to be motivating. And but if you're very interested in this field, there will be enough ideas of where to go and what to do if you want to dive into the technical knowledge and into the field. So, but before we move forward, I'd like to take a step back. I think this picture is a really good illustration. It's a horse car from the late 1800s. And just like back then, we're at the start of a paradigm shift in mobility, where they substituted the horse with an engine. We are substituting the driver with a computer. And so everything we'll talk about today revolves around this paradigm shift. And I'll try to give you my perspective on it. But before I'll talk about my perspective, how do you imagine a future with a self-driving car? Like what is it for you? Just think about it for a second. Do you imagine working on your commute? Maybe taking meetings on the road? Or do you imagine having your groceries delivered by the time you arrive home? Or do you imagine our cities changing? There are, in fact, a lot of people working on realizing these visions, and that kind of future is not so far away. According to an Intel study, I think it's 1 year old or something, a new passenger economy enabled by autonomous driving will in 2015 be worth $7 trillion US. So it's an industry and market which is emerging almost out of nothing, enabled by autonomous driving. And in California, there are now just 53 companies that have acquired licenses to test self-driving cars. These are all the companies in the way they got their license. So California is really proving to be the focus area for this research. So, so in terms of the societal perspective, I like to say that Kløfta will be the new Oslo city center, because you can go in your car and start working, and you'll be very fast into the city. So cities, you will see cities expanded, and the cost of houses will go down. And according to World Health Organization, in 2015 there was 3,400 deaths each day by traffic accidents and 50,000 injuries. So imagine all these lives. It's kind of 1.25 million lives each year with, by death in traffic. You also have the financial aspect of this as well. There are a lot of costs involved with this. And obviously, cost of mobility will be reduced, and suddenly people which can't be mobile, like blind, elderly, young, and disabled, can now go about and go around. And just like you now take it for granted to be connected with the rest of the world via your phone or your computer, in the future you will take it for granted to be mobile. You will be seen as a human right almost. So, so in this course we are working with robotics, and so what is really a self-driving car? I find this very intriguing because it's just another robot. In fact, it's a mobile ground robot. And here you can see the pipeline, where we have the big three parts of robotics, where you have the perception, planning, and the control. Perception, planning, and control is the three big parts of a robot. In this course, we have worked a lot with control. You have simulated or tried to model the dynamics of a system and try to control it with, for example, a PID controller. You have not worked on path planning, but you have learned to model the kinematics of a robot. So, for example, if I say the robot is like this, and I give you the joint variables, you are now able to calculate the point in 3D space, right? And then if I give you another joint angle, you can be at another point. And if I give you a set of joint angles, you will get a path in 3D space. So using the kinematics, you can do path planning. And in fact, on page 365 in your book, there is a model of the kinematic car. And I'll try to briefly draw it for you. So you will have so just like we describe a regular robot for our sake, maybe it's like theta 1, L1 star, and theta L2 star, and theta 3, for example. In the kinematic robot, we are interested in this angle here, phi, and we are interested in, well, if this is a line parallel here to the x-axis, here we are interested in this theta here, and then this will be an x position, and this will be the y position. So the configuration variables will be x, y, phi, and theta. So this should be seen familiar with regards to robots like this, which we have worked on. So that's path planning, and control you will work with in the next course, Unique 4490, control of manipulators and mobile robots. You will also work some with localization. Localization is, for example, GPS, but GPS is not accurate enough, so there are a lot of other techniques used as well. One is odometry, but it's not superior to GPS. But there you use the wheel circumference and try to calculate how far you have traveled with the car. Sensor fusion is the part where you take all your sensors and use a particle filter like the Kalman filter, and you fuse those together. Kalman filter is you have extended Kalman filter, and you have a lot of other Kalman filters. But yeah, there is a course on computer vision, Unique 4690, which covers, I think, some Kalman filter and basic computer vision. And what's happened in recent years now, this is not anything new. people have been very good at this since the 80s. But the thing is that the perception part, where you try to perceive the world through a camera in computer vision, you're starting to use techniques like deep learning and stuff, and you try to understand the scenario. And that's what's enabled this shift in technology. Okay. Yes, and worth mentioning that in this course we have worked with set point tracking systems. So if you have a desired value of 40 here, no, actual value of 40 and a desired of 50, then you maybe are doing something like this. And then this desired here is a step input. So, but for self-driving cars, now this desired value is a trajectory. So now we're continuously changing it. And that's why you see on this slide here from the control theory part that we like just make this imaginary. The desired value is not changing, it's constant in our course. But in the next course, and for mobile robots in general, you will have a changing desired trajectory. Okay, so before we start to talk about the different players and what the status is, we need to have some definitions on board. So these are definitions which you may have heard, and unfortunately a lot of those are covered really bad in media and things. It's the Society of Automotive Engineers. It's a worldwide society, and where you have a level 1 autonomous systems, you have a hands-on feature. So, for example, adaptive cruise control. That is a feature where you steer the car and you maybe set the distance to the car in front, and the car holds the distance itself. So you need to have some sort of control over the car. Level 2, it's a hands-off system where you can completely remove your legs and hands, and the car is able to drive itself. But like level 1, level 2, you need to continuously pay attention, and you are always responsible. And it's a bit, the definition is hands-off, but the different manufacturers, like for example Tesla, has this in X, the 3 and S, the 3 and X. They say that you have to hold your hands on the car, on the steering wheel. That doesn't mean that the car is unable to steer by itself. And in fact, you can see crazy videos of people putting themselves in the passenger seat and the car is driving itself with no one in the driver's seat, and that's crazy. But that's a level 2 system, you're always responsible. And the level 3 system, you have some time before you need to take over. And before that, it's fully self-driving. But when it says you are responsible for the situation. And Audi is claiming that they have a level 3 system. And I think, like legally speaking, they are right. But the flaw with level 3 systems is there is no, you haven't set a time. So you can have 10 seconds, you can have 1 second, I believe there's 1 or 3 seconds. So their system is really not actually superior in no way to the Tesla system. And their system is limited to 60 kilometers an hour only on highways in certain areas. So do not be fooled by achieving these categories. And it's not like more autonomy, it's different approaches to autonomy. People think like, oh, because you can have a really good level 3 system. So level 4 is the most common, which is the most important to know about. And this is a fully self-driving car within a geofenced area, for example. So, for example, within Los Angeles or Oslo or something, or under certain conditions, for example, weather. And level 5 is fully self-driving everywhere, anytime. So level 4 is what's been aiming for by most people. Okay, so these are the top players in the field, and now we are talking about the technology. Here we have Waymo, which is the former Google X company. Tesla, GM, Baidu. We will talk about all of these, Ford and Sux. It's like whether there are like these or it's not really, but Waymo is certainly the tech leader and has come farthest with the technology. They have very heavy focus on simulation. Every day they have 25,000 cars running in a simulation. So they have total driven 4.4 billion kilometers. And in real life they have done, I think now it's more, but around 8 million kilometers. And in this 8 kilometer, they have a really low disengagement rate. That means when the rate which the driver needs to, the safety engineer needs to take over, and the vehicle isn't doing the correct thing. So 0.18 disengagements per 1600 kilometers. They have already launched a level 4 system in Phoenix, Arizona, last fall. So Waymo is already at level 4 and working on deploying. So they have test families, which I will have a picture of. And later this year, it will be commercially available for everyone, the public, in this area. So they are aiming for ride sharing in certain areas. Yeah, and they have over 10 years of experience. They are former Google self-driving car project, and this is a really big advantage for them, because what's driving this revolution or technology shift is AI, and Google is by far one of the most biggest players. Okay, I think we'll start again. So for the break, we looked into the DARPA challenges. We looked at the people participating in the winning teams becoming the backbone of the self-driving car industry. We looked at briefly on the status of self-driving cars today, and that it takes a whole industry to make self-driving become real. We reflected some on what we can do and what advantages we have in Norway. And from all this, I would like to make some predictions. From this, I think we can very easily predict that a high-stake competition like the DARPA challenge will create talent in the field of the competition, as we just saw. And then also, if such a competition has a fixed set of hardware, the challenge will be about the software. And if that hardware is similar to what's used in self-driving car, you will create relevant competence in the field. And in fact, those predictions I did before I discovered, long before I discovered RoboRace. Have you heard of RoboRace? This I can try to show you some quick movies about RoboRace. Let's see if it works. So this is a company in England which is making autonomous competition.
I'm Bryn Baucom, I'm Chief Strategy Officer at RoboRace. You can see the Robo car behind, which is a fully autonomous Level 5 racing car. And we have a great partnership with NVIDIA on the technology that sits inside the car. Traditional motor racing, if you look at circuit-based racing, it's almost identical cars following each other around. From an autonomous point of view, it's really like a Level 2 challenge. You know, it's kind of lane keep.
Adaptive cruise control.
And adaptive cruise control.
Adaptive cruise control is not the level 2, it's a level 1, so he's saying wrong, but yeah.
What we're looking at is trying to be a level 5 competition. So we're talking about real road environments with these cars racing through traffic. So trucks, buses, cars, motorbikes on the track at the same time, with these cars racing head-to-head through the traffic. The environment that we're creating is really a future vision of the roads. And if the car can do it in that environment, then it's going to drive you safely around when you're going down to the shops or to school or to work. The big change for us now is to move to the NVIDIA Drive Pegasus platform. That's really the central hub where we integrate all of the cameras, radar.
What he's talking about now is moving to NVIDIA Pegasus platform. This is the new platform from NVIDIA. It's not new, but previously it was the Drive PX and the Drive PX2. Those are chips that, like you maybe heard of for GTX 1080, like a graphics card for computers doing deep learning. And Drive PX and PX2 is the card for self-driving cars. And Drive Pegasus is the new stuff, which is insane. And that's why what's he talking about now.
LiDAR, sonar, machine vision cameras, and then the GPS inertial system. That means all of the sensors can now improve because we've got the bandwidth going into the central compute platform. And it's incredible because it gives us new opportunities. The Pegasus platform is really the leading edge in compute for autonomous vehicles.
Okay, so I think this is very interesting because this is a race where you in the future could team up, work on this car, race around the track, and then try to compete. And it's really interesting because it's the exact same assumptions and predictions, assumptions they have done. And this comes a bit into, I forgot to tell you, but I will talk a bit about my own work. And in my own work, I have a proposal for a Norwegian challenge where there is a fixed set of hardware requirements close enough to what's used in self-driving cars today. The vehicle is compatible with existing robot championship. So there is, in fact, like you have the Olympics, you have 400 meters, long distance jump, heckler, I don't know the terms, height jump. You also have these kind of robotics championships, and there is in fact one class originated in Sweden called Folk Race, which you have small autonomous cars driving around like this. So it's very fun for the kids and very messy thing. And here there is people who invest 500 kroner to people who invest 5,000. This is held yearly in Sweden, in Göteborg and Stockholm, and we are a couple of guys at Bitprof, which regularly go there. I wasn't this year, but yeah. So if this vehicle is compatible with this type of class, I think it's also cool to show you. This is another type of class, which is called sumo robots, which is really huge on world basis. So just like sumoing, you try to push the robot out of the ring, and the first one wins. And like these are a real serious deal. So you can find all around the world competitions like these sumo. It's insane. And you have all classes from these types of sumos to these types of sumos. Okay, we can watch this all day, I think. It's just to illustrate that there is actually a kind of Olympics for robotics, and these are some of the classes. And I propose a challenge where the vehicle is compatible with this. Here is the Robot SM in Sweden, and Robotics in Estonia is Europe's largest robot competition. If the challenge has a high stake, high reward, like the DARPA challenge, like you really have to work really hard and you get the high reward, and the participation is open for everyone in Norway, students in Norway. It's held annually and it's organized in such a way that it facilitates research on the challenges for self-driving cars. Such a challenge will facilitate competence and talent in the field of self-driving cars. That's my proposal, and that's the basics for my research on Reaper. So here I'm creating a self-driving small mobile robot where I'm using NVIDIA Jetson TX1. It's this chip right here. This kind of laser, HUQ, I never can say the name, structure IO. I base it on competition-based RC. So RC cars, there are a whole ecosystem of championship in RCs. So certain models, there are a lot of parts, and yeah. Also have another type of LiDAR, which is not, and the front-facing camera, which is not on this picture. And the interesting thing with Reaper is, unfortunately, I couldn't bring in today. It's in a million parts, but it will it will enable all these checkpoints, various requirements for the vehicle. And the reason I call it a realistic approach is that you cannot really work with Arduino and sensors and stuff like that for a couple of $100 and expect to be cutting edge in a field of self-driving cars. You need to have some sort of go higher in the technology, and Reaper is, in my opinion, the lowest you can go. This costs around 30,000 Norwegian kroner with everything. But imagine a self-driving car where, like for GM, where you only for, so 30,000 Norwegian kroner is about $5,000. GM's LiDARs are only LiDARs are costing 30,000 US dollars. So imagine the whole car. What's interesting here is that I can, when I develop my neural net, I can directly take it from this chip and put it on the NVIDIA Drive PX or Drive PX2. So the architecture in this NVIDIA chip is the same. So I think it's very cool, and yeah, it's my research right there. And so if you're interested in self-driving cars, there is I regularly come about this service where people go through job postings, and here you have 8 companies, and you can see what kind of skills you will need to work with self-driving cars. And it's really C++ is really the language to know. Machine learning, obviously. This is a more representative approach because here is only 8, but you have 8 of the big ones: Tesla, Ford, and Waymo, such like that. Cruise, that is GM. So Python, which we learn a lot here at the university, is okay, but C++ and C are really the programming language to be fluent in. And if you are more interested in self-driving cars, you can, I think, spend a couple of days going through the hidden links in this presentation, and yeah, reading about this. There are a lot of hidden links which you may or may not find. So, do you have any questions? No? I think we need to develop self-driving cars here in Norway, or else we won't get the service to go where we want to go. You know, Waymo is only mapping and working on very nice weather and conditions, and that is not what we have here in Norway. Our conditions are very hard, so we may encounter a HAL 9000 scenario if you have seen Space Odyssey. Okay, that's it. So, and I think we'll